I'm very sorry about this, and if you have something that you have to leave for at 11:15, I understand. I will still record it for 1 hour 15 minutes, and then so if you have to leave at 11:15, I completely understand. So what I am planning to do today is to start talking about the planning graph heuristics that we started discussing in yesterday's class. Okay. The first thing that I want to just remind ourselves, so 10, 20, 11, 20, and 11, 20. So 11:35 we should be done. That should be the correct thing. Okay. So first thing I want you to remember is we were talking about. Oh, it works too. Wow. Okay, so first thing we realized that for us to do anything at all, the entire internet should be working, because right now I'm logged on to my office machine and I'm using remote desktop. So anyway, we were talking about the symmetric set difference, the set difference heuristic, and why that's not good, and that in fact heuristics that might actually take more time to compute might actually be more powerful. Okay. That was what we discussed, right? And so the first thing is we did talk about this idea of subgoal interactions yesterday, and we said something about negative interactions. If you ignore, so we talked about independence, positive and negative interactions. Before I go forward into the heuristics itself, it's what getting this idea into your head. Most planners, basically, when you have set of subgoals, the simplest assumption to make is that the subgoals are all completely independent. That means the progress you make on one of the subgoals does not affect either positively or negatively the progress on other subgoals. So it really is like I have two different things to do, and I can do this and I can do this, and how I do this does not have any impact on this. That's independent. Okay? Positive means the certain ways of doing this that will also help this. Okay, negative means there are certain ways of doing this that make it harder to do this. Okay, and in your common sense, real life, you can come up with examples for independent subgoals, positive interaction subgoals, negative interaction subgoals. Okay, one thing worth remembering is that if you, in fact, in terms of the lengths of the plans, if you have a plan which basically, for each of the subgoals, G1 to Gn, suppose you have plans L1 to Ln. That means, plans of lengths L1 to Ln. So the G1 can be solved by a plan with length L1, and that of G2 by length L2, and so on. Okay, so then if they really are independent, then if I tell you how to solve each of the subgoals, you can solve the set of all subgoals by just concatenating these plans, essentially. In fact, you can throw them together in any which way. If they are really independent, it doesn't really matter how you put them together. So you can do one of the actions for this goal, one of the actions for the other goal, come back to the other action for this goal, and keep completing all of them. And when you're done with all of them, all goals are satisfied. Okay? So the total plan length will be L1 plus L2 plus etc. up to Ln. Right? That's the intuition you have, and this is actually the more formal way of saying that if you sum the plan length, then you will get the length of the set of goals, set of all goals. Okay. If on the other hand you have positive interactions alone between these subgoals, then the true plan. So basically, in some sense, you're trying to guess the. You'll notice today that one of the interesting things is estimating the cost of achieving a set of subgoals when I know how to achieve each one of them separately. That's an interesting issue. That's where you need to take interactions into account. And I'm saying that if they're independent, you can just add them up. Summing would work. Okay? If on the other hand, if there are positive interactions and you sum them, then you would actually be overestimating the cost. Right? Because because satisfying one of the goals will actually wind up satisfying another goal too. So you would have been overestimating. So really, if the true cost of all n goals is strictly less than the sum of all the plans, if you have positive interactions alone. If you have negative interactions alone, then the true cost of satisfying all n goals is strictly greater than the sum of satisfying the cost of satisfying each of them, the sum of the cost of satisfying each of them. Does that make sense? Okay, and in general, this could be L1n is less than this. So in fact, one thing you can see is you can actually, if you were to take the maximum of these lengths, that means, you know, the first goal, it requires 10 steps, second goal requires 15 steps, third goal requires 19 steps, and so on. I'm not saying max, actually, I should say min. So, no, max. So if I were to take the number of steps for satisfying any one of those goals alone, and suppose that is 30, then I know that the total plan cannot be less than 30, because you need 30 just to satisfy this one goal. So if there is a maximum amount of positive interaction, everything else also just magically becomes true when you satisfy this one goal. So admissibility, to get admissibility, you typically take the max of the costs of solving each one of the goals. Okay. If you have, you know, negative interactions, then essentially the true cost can be arbitrarily larger than this, you know, the cost of satisfying any one of these goals. In general, it can be infinite. So, for example, I can, you know, in simple blocks world, it's very easy. Simple blocks world, I have A and B and C, right? It's very easy to get on AB as a goal, no problem. I can also get on BC as a, on BA as a goal, no problem. But if I need to do both, the cost is infinite. That's where you have negative interactions. I mean, that's the extreme form of negative interactions, but there are other kind of negative interactions. In general, negative interactions increase the cost from this summation. And the positive interactions reduce the cost from this summation. And in general problems, some subsets of goals will have negative interactions, some subsets have positive interactions, some subsets are independent. That's how you're stuck with. Okay, this is an abstract level where you're assuming either they're all independent, they all have positive interactions, they all have negative interactions. But in general, it's somewhere in between. So which is why the length of the plan for solving a set of goals can either be less or greater or equal to the sum of the lengths of solving them. And, you know, we're trying to get the estimate on that. Okay, and in trying to get the estimate, as long as our estimate is less than the true cost, will be admissible. If it is too less, it won't be very informed. Because 0 will always work, but that will not be informed. Okay, so that is basically, you know, about some goal interactions. So anyway, we already looked at this simple idea of, you know, just counting the number of goals that are missing. Okay, which are in the current state. That's the set difference heuristic. And we found yesterday that there were two interesting issues. There are two interesting issues about, by the way, this I added after the class because we discussed about this whole NP completeness, P-space completeness. So it just summarizes that. So when we were looking at the set difference heuristic, we looked at, is it admissible? And it's not admissible because they can have positive interactions, and when you're just considering each of them separately, you're assuming they're independent. And when I said, is it informed? And I said it's not informed because separate subgoals might require longer plans. So remember, if you just assume each goal counts for one unit, then you're assuming in that previous slide, L1 is 1, L2 is 1, L3 is 1, L4 is 1, etc., Ln is 1. That means all subgoals just have one sized plan. That's not true. L1 can be 15, L2 can be 35, L3 can be 49, and so on. Some goals are harder to, you know, achieve than others. Okay, and furthermore, not only is it missing that part, it is also missing the part that if L1 can be done in 30 steps, L2 can be done in 40 steps, L1 and L2 may require 170 steps because they have negative interactions. So those are the things it was missing. So we have overanalyzed why this idea didn't work. The reason we overanalyzed it is because we'll get to this next one, which looks as if we're doing a lot of work, but it takes care of all these problems. Okay, so that's basically the planning graph heuristic. And so to do that, actually, I will take a even simpler example. You know, we had looked at Bloxworld example before. Okay, I will come back to that in a minute, but we'll see in a minute, you know, that this is an even simpler example because it's easier to write the pictures for it. Okay, so this is basically directly from the textbook. So it's a simple problem where you apparently in the initial state you have cake. In the final state, you want to have cake, and you also want to have eaten the cake. You know, that's what your mother told you cannot be done. You know, you can't have the cake and eat it too. But you know, of course, if you have a cake making apparatus, you know, such as an oven or something, you can eat the previous cake and make a new cake. That way, you'll have both have eaten a cake and have a cake, right? Okay. And so I have two actions here: eat cake action, which requires that you have the cake, otherwise how are you going to eat it? And then the effect is you no longer have the cake after that, eating it up, okay? And then you would have the full satiated feeling of having eaten the cake, okay? The other action is bake the cake, which for whatever reason, you know, I guess I'm being extremely, in this action I'm saying you cannot bake the cake unless you don't have the cake. I mean, that's like, you know, your mom saying, you know, don't make too many cakes, you know, just one cake, eat it, and then make the next cake. There's no real reason why this action should be this way. It's my domain, I made it up. So in this domain I said, you must not have a cake when you're about to bake the cake. Otherwise you'll be like one of these cake ladies with too many cakes at home, okay? So you don't have a cake, and then your effect is you will have cake after you bake the cake. Simple enough problem, right? And then, of course, initial state is you have cake, and you have done, since you didn't say anything about eaten, that means you not eaten cake is true, right? Because that's basically the way we think about the states. Okay, very simple problem. How many variables? How many fluents are there? How many state variables are there? Just two: have cake and eaten cake. That's it. That's why I picked this. You know, the Bloxworld has already 10 state variables, and you'll see when I'm doing this analysis that the pictures can get pretty complex. The computer program has no problem, but if you are writing it on the board, it becomes very busy. That's why I'm looking at an even simpler problem. Okay, so now I want to figure out, given a state, I want to figure out how far is it from the goal state. Right? That's the basic idea. I want to figure out how far is a particular state from the goal state. Okay? Suppose I give you, just happen to give you the state, the complete state, have cake. I want to know how far is it from the goal state. Okay, so let's start with the dumb idea. Okay, the dumb idea is so have cake and not eaten cake, right? Of course, in the beginning, right? So then I'll just figure out how far I am from the goal state. I will actually just go ahead and do the full progression planning from here. Okay, I said it's a dumb idea. Okay, so if you do eat, you'll get this state. If you do nothing, you'll get this state. Okay, I will, for reasons that become clear to you, you always have the option of doing nothing. Nobody ever tells you that, but I mean, you know that. I mean, many a time, that's what you're doing nothing, right? Right? And if the world is not dynamic, if you do nothing, the world remains the same. Unfortunately, the world you live in is dynamic, and you do nothing, the homework deadline comes and goes. And that's not good. Okay, so since we are in static worlds, do nothing is an option. And we just don't consider it, but it's a reasonable option. It is an option. Okay, so if you eat, you will be here. If you don't do anything, you will be here. Okay, now starting from here, if you bake, you will be here. If you do nothing, you will be here. And then from here, if you eat, you will be here, and you do nothing, you will be here. This is the set of all states you will get for this little problem. Okay, now I can see basically my goal is have cake and eaten cake. Have cake, eaten cake here. So I know what is the shortest path, 2 units. Right? So now I can say the heuristic, assuming that you assume that all actions are of the same cost, that's what we are assuming right now. Okay? Then the heuristic cost of this guy is 2 units. What did I compute here? I computed H star. nobody in their right mind would compute H star, because H star essentially would be as hard as the original planning problem. So in general, had this been the Tower of Hanoi problem, and you have 64 pegs on one, and then there's a middle peg that's empty, and there's a third peg that is empty, and you're asking yourself, exactly how many steps do I need to have all of these transferred to the third peg? You would draw this for 2 power 64 levels, a depth of 2 power 64, and then you'll say, yeah, there is a solution. And so my H star is 2 power 64. Okay, and so in general you don't do it, but this is so what I need to do is, this is the full reachability analysis. I use the word reachability. That means I'm trying to figure out how far do I need to go to reach the goal state. Okay, what I want to do is, I want to approximate this somehow. Okay, because after all, doing it full, it's H star. I want to approximate it. Think of pattern databases. Okay, in the case of pattern databases, the pattern is the full board, that's H star. If the pattern is just a fringe, that's an approximation. And it's an approximation that has the good property that the length of solution to get the pattern is going to be a lower bound on the true cost. And furthermore, it would be better than number of misplaced tiles heuristic and the number of and the sum of the Manhattan distances. Okay. By the way, okay. So I want to just somehow approximate this, and here is the way I will approximate this. Okay. What I want to do is act like this. Suppose I were to somehow think of a way in which I don't draw the whole tree. Instead, I just draw one proposition list per level. Notice that this is level 0, level 1, level 2. Okay, and there are like membranes which is separating each state from the other state. Suppose I somehow magically disappeared the membranes. Okay, then I just have a much simpler data structure. I'll say have cake, not eat cake. I'll just say HC and not EC to make it easier. Have cake, not EC in the first level, right? In the second level, I'll just union all of these. Okay, so not HC, EC, HC, not EC. Clearly this is not a state. Clearly this is not a state. Okay, but why is this useful? For example, if suppose I'm trying to figure out a particular state variable, I want to have a particular state variable to have a particular value. Okay, if it's not present here with that value, that means the smallest length plan is still larger than this number of levels. I'm putting a lower bound. If you're present here, so for example, have cake is present here, so that means you can get the plan in length 1 or more. Whereas something like a TC, I don't know what TC is not present here. It's a different variable and its value. TC being true is not present here. That means it requires a plan of length greater than 1. Do you see what I'm saying? And furthermore, one other interesting thing is, if I have not have cake and eaten cake in this state, that means I know exactly I have a length 1 plan to get to that state. Consider this. It says I have a not have cake and have cake both. Suppose I needed both of them. According to my analysis, I will think there is a 1 length plan that will get me, because they're both there. But what that analysis is missing is there are negative interactions. But negative interactions will only increase the length of the plan. They can't reduce the length of the plan. Right? So I will still be a lower bound. Okay? So if you think about it, whatever crazy thing I'm doing, which is somehow, puddling these things together into a single proposition list, will give me useful information about a lower bound information about how hard is it to achieve different goals. Okay? Now the question, of course, is how do I construct this? So of course, next level of this would be HC, EC, not HC, EC, HC, not EC. And of course, this is a set, so there's an HC already, I don't need to write it once more. There's a not EC already, so there is 2 ECs, so I just need to write one of them. Here is an interesting thing. From this level to this level, has anything changed? So, is there any point in going one more level after this? No. Because by here, if you have n Boolean state variables, you already have 2n elements here. That means for each element you are saying both positive and negative. Even if you did not say it, first of all you are saying it here, that's why there is no point in going forward. Even if you did not say it here, one of the interesting things is, we'll see in a minute, that by construction, this structure has the property that you are acting as if every action that is doable at all can be done, even if in fact it is interacting with the other actions being done parallelly. We'll see that in a minute. And if so, if with that amount of relaxation you don't change from one level to another level, then there is no more point in extending the graph structure, because it's not going to change ever again. So unlike this, which might keep going for quite a long time, these can level off. The graph structure can level off. And you consider it to have leveled off while you are constructing, if in fact there is no new proposition entering the proposition list. We call these proposition lists. You don't want to call them states because they're not states. They're basically unions of states. And unions of states don't have right properties. In fact, they're upper bound union of the states. And so you call them proposition lists, and if the proposition list doesn't change from one level to other, you can stop. And once you do stop, then you can use this structure to answer queries such as, how hard is it to make a particular goal true? Well, you start from here, go on the proposition list until you find that goal present in a proposition list. That's the lower bound cost. The length, the index of that level is the lower bound cost. If the goal that you want to make true is only present in the 15th level first time, then it at least takes 15 units. What's more interesting is this structure has humongous redundancy. Because I throw in no ops everywhere, if I do get something to be present in the 15th unit, 15th level, then we present 15th, 16th, 17th, 18th, 19th, 20th, etc. Once you get tenure, that means, this is basically an academic thing. I mean, once we get tenure, you will keep seeing us year after year after year. Okay? So once a proposition comes into the proposition list, it will never go away. Because you can just do nothing and keep it. Okay? So that's the basic idea of the structure. The big question is, how did I make this structure? The way I made this structure right now is I made this structure and unioned it. That's not dump, that is dump plus plus. Right? Right? Basically, not only did I do the H plus, I threw away the H plus and made a dumper version of H plus. And it takes more than the time required to do H plus and does less useful information, gives me less useful information. So for me to make sense at all, basically this should be constructible directly, not from there. And thankfully, yes, it can be constructed directly, and furthermore, it can be constructed in linear time. Okay, that's the advantage. Okay, so see what happens. Here, so basically instead of that, I'm going to again take the same example. I put the example up there, and I'm showing you how the planning graph is constructed here. Okay, step by step. So you start with the initial proposition list, which is just the initial state. Have cake, not eaten cake. Now you throw in every action So then you have proposition layers, action layers, proposition layers, action layers. So planning graph is an alternating layers of propositions, actions, propositions, actions. In the action layer, I will put every action whose preconditions are already present in this proposition list. That means it's sort of possibly doable. Not definitely doable, but it's possibly doable. Why it is possibly doable? Because suppose you make a magical action which requires both HC and not HC as its preconditions. In the real world, that magical action can never be done. But here you would throw it in because there is HC and not HC. You see what I'm saying? So you actually try doing more actions than are actually feasible in the real world. But that's fine. That will only make you feel as if the planning is easier than it really is, and that way you'll never go wrong in admissibility. Okay, so anyway, so I put these three actions. Okay, I can do eat cake because eat cake only requires have cake. I cannot do bake cake because bake cake requires not have cake. I still don't have not have cake in this proposition list. As you know, it's like you have as relaxed as this structure is, it still has some rules. Okay, it's saying I don't have not have cake, so you can't put bake cake here. So I threw in eat cake. Okay, and if I throw in eat cake, and first thing I'll do is I'll put in eat cake. I will put a link from have cake to eat cake action because it's a precondition. Okay, not particularly hard. And then I will, if I do eat cake, I will get all the effects of eat cake. Eat cake will give me an effect not have cake and eaten cake. So I throw them into the next proposition layer. Okay, and I remember that eat cake gave me these by putting those links. Okay, forget about these things for now. Those curved links, don't think about it right now. We'll get to them later. Okay, and then eating cake is one way, but then remember I want to handle no ops. Anything that I had before I should be able to continue to have by just not doing anything. So I will essentially consider a special set of actions called persist P, which requires P and gives P back. That's a cheap way of copying everything that was true before. So apart from all the actions you have, these two actions, you assume for each proposition true false value, there is one persist action. And all it does is it requires that has that value, and it will continue to have that value in the next level. So here, this persist action is basically requiring have cake and will have cake back. And this one is requiring not eaten cake and will give not eaten cake back. Okay? And so now basically you have constructed a planning graph of one length already. And that basically corresponds to this here. I did not have to construct the projection graph first. Right? I just did this directly. Okay? And then now I do repeat the same process from here again. Okay? So I will, you can see now that planning graph problems are not pretty. If you have to write it on the paper, it starts becoming quite busy looking structure quite fast. But for a computer program, who cares? You can put all sorts of links in a data structure. Nothing actually happens. So here, for this problem, basically, now I can do both bake cake and eat cake. I can do both bake cake and eat cake. And so bake cake will give essentially have cake. Eat cake will give not have cake and eaten cake. And everything that's here will be persisted again here. Now what's interesting now is previously you only had one way of having cake, which is to have persisted it from the previous level. Now you have two supports for have cake. One way is you had cake and you didn't eat it. So you had cake and you continued having it. The other is you baked the cake. Okay, so that's what the structure is telling you. So in some sense, one of the things that's happening is some things may be present here and they will come again be present, and anything is present here will be present here too, but it might have more support. So there are more ways of making it true. And that winds up being useful, as we'll see later on, when there are negative interactions. Okay, in fact, actually just jumping ahead, you can kind of see that having cake and eating, have cake and eaten cake are not together possible. You know this intuitively. And we will talk about an idea called negative interaction propagation or mutual exclusion propagation, which will allow us to mark actions that are mutually exclusive and propagate those mutual exclusion to whatever they give. So for example, again jumping ahead, and I'll say it again later, eating cake action requires having cake and removes having cake. So you really cannot have eating cake action be done parallelly with having cake action. Because this guy's effects are contradicting this guy's effects, directly contradicting. So they cannot actually be done parallelly. Okay? So you could mark, you can make a little mark saying, well, these two guys are mutually exclusive. Okay? And then once I have that simple marking here, I can now propagate this and say, if this guy cannot stand in the same room as this guy, then if this guy is the only guy giving eaten cake, and this guy is the only guy giving have cake, then they can't stand together. Right? That's mutual exclusion propagation. So that analysis will allow you to realize that by second level, even though have cake and eaten cake are present, they happen to be marked mutually exclusive, so they are not actually feasible yet. Now by the time you come here, they are no longer marked mutually exclusive. Why? Because one way of having cake, which is have cake, is still mutually exclusive with one way of eating cake, one way of eaten cake, which is eat cake. But there is a different way of having cake, which is bake cake. That's not mutually exclusive with eaten cake. So for two guys to be mutually exclusive here, this and this to be mutually exclusive, every way of making this guy true must be mutually exclusive with every way of making this guy true. That's like n square combinations. If all n square combinations are mutually exclusive, then they are mutually exclusive. This is what you do in marking the mutual exclusions. And if you do mutual exclusion propagation, then you are doing negative interaction analysis. If you don't, then you still have done positive interaction analysis. Why? Because if two things, if one action can give two things together, you would realize that quite easily in this structure. Okay? So, and by the way, so the negative interactions, will come back to it towards the end of the meeting again, but for now just focus on the positive interactions. Okay? Negative interactions will improve the informedness, positive interactions will just ensure repeatability. Okay? Analyzing the positive interactions. Any questions on this? That's the structure. That's what we're going to compute. Okay? So it should be possible to write a program which starts in the proposition list, throws in all actions whose preconditions are present in the previous level, throws in all their effects into the next level. There's only one level here. There are not many states. There's only one level here, not many states. And if between two levels nothing changes, you stop expanding the graph. Since we are also talking about mutual exclusions, then you can't, if you're also doing negative interactions, you can't stop just because things didn't change from one level to other. Like for example, from here to here, no new propositions came in. No new, propositions came in. But a mutex went away. That's change. You see what I'm saying? In fact, if you're seriously doing negative interactions, one of the things you will say is you are not allowed to put an action in unless its preconditions are present in the previous layer and no pair of them are marked mutually exclusive. That's reasonable, right? I mean, if I already have marked mutexes saying these pairs cannot be made true together, and this action requires PQR are present, but P and Q are mutually exclusive. So you already know that this action cannot be done. So you won't put it in. Now that that mutex went away, that action can come in now, next level. And so it can then bring in its effects. So when you have mutual exclusions, you would essentially continue expanding the graph until again there is no change from one level to other level. And the change is no more new propositions are coming in, and no mutexes went away. You see what I'm saying? No mutexes went away. One of the interesting things is there is a tenure system for propositions. Once they come in, they never go out. What about the mutual exclusions? There is also a tenure system for them. Once they go away, they'll never come back. If two preconditions, so if by this level you figured out a way in which having cake and eaten cake is possible together, I argue that from now on until eternity, you will always have a way of making them true together. Why? Because now that you have both of them, just keep doing no ops. The same no ops. So just as propositions will once come in, they won't go out, mutexes once they go out will never come in. And so if in fact mutexes, if from this layer to this layer, no mutexes went away and no new propositions came in, then you say the graph has leveled off. And then you don't need to expand it any further. Okay, that's the full graph construction, by the way. Since I actually, having said I would do mutual exclusions later, I actually spent a lot of time explaining to you mutual exclusions. So, in fact, let me just tell you the details of, the full set of details of what we did here. You would be, let me just go to that slide. I was going to do this later, but I'm just going to do it now. Okay. So this is basically the mutual exclusion analysis that we were doing. The same graph, the moment I put this label, I realized that eat cake is mutually exclusive with this no op because it has either preconditions of this action are directly negating the preconditions of the other action, or the effects of this action are directly negating the preconditions of the other action. When you're doing things parallel, it's possible that you serialize them in the wrong way. In which case, if you did this epsilon time before this, then this would have eaten up this precondition, then you can't do this anymore. Okay? So whenever the preconditions are, either the preconditions of these two actions are mutually inconsistent, that means one requires F, one requires not F, or one of the guy's effects is mutex with another the guy's preconditions, you don't put then you mark them as mutually exclusive. Once I mark them as mutually exclusive, at the next layer, for every pair of propositions, if every way of supporting this proposition, this is where these links help. Every way of supporting this proposition is mutually exclusive with every way of supporting this proposition, then you put a mutex link. And you continue. Okay? And so in this case, basically, if you go to this next level, you should make sure that you understand all these links. It's basically, this is stuff that computers can do. It's just a series of rules. They just have to do repeatedly. We, on the other hand, can easily, make silly mistakes after a while. Okay? But so you just need to understand, it's not hard to do for a program. There are many things that are not hard to do for programs. And we are computer scientists. It's not what's hard for us, it's what's hard for the program that we care about. Right? And planning graphs are a classic case of things which are actually harder, for some people at least, to conceptualize up front. But they actually take less time to compute than the full projection. Not just less, they take exponentially less time to compute than the full projection graph. Okay? And then, so these basically are the rules that I just mentioned. You can mark any action, which if the action A1 is any action supporting P, and action A2 either needs not P or gives not P, then you will say it has interference. And so you consider them mutex. And similarly, if some precondition of A1 is already marked mutex with some precondition of A2, then those two are considered mutex too. So for example, this guy requires PQ, this guy requires RS. I mean, this guy requires PQ, this guy requires RS. You already marked Q and R are mutex. That means these two actions cannot actually be done together. Did you just see what I said? So this action requires PQ, and this action requires RS. But your analysis, you're somewhere in the middle, okay? Your analysis already has shown that Q and R are mutually exclusive by here. Which means A1 and A2 cannot be done together. Again, you're just propagating, consequences. This is sort of like spreadsheets. Spreadsheets basically propagate the consequences to next layer and so on. So the spreadsheet metaphor is not at all the wrong metaphor. That's exactly what you're doing. You're doing constraint propagation. Okay. There is this one other thing, the textbook also talks about, which is if you actually are assuming that you are counting the length of the serial plan, that means you're not allowing parallel plans, then you want the number of actions. And so in that case, you might just assume that any two non-no-op actions are mutex. That means if you can only do one action per time step, you can assume that any two non-no-op actions are mutex. That way you will get an estimate on the serial plan rather than parallel plan. Okay, parallel plan basically just tells you how many layers, but each layer may have 15 actions. So I can have just 2-layer plan, so you would think the length is 2, but then the first layer has 15 actions, second layer has 17 actions. The total number of actions is 15 plus 17. So you are actually wildly underestimating the true cost. It's still admissible, but not very informed. So, this serialness will actually take care of that if you throw that in. Okay, we'll talk about a different thing which also does the same thing when you don't have negative interactions, called relaxed plan extraction. Okay. And then the second rule is, this is for the action mutexes, how actions become mutex. And then action mutex is then propagated to the propositions. And the propositions become mutex. P1 and P2 are marked mutex. If all actions supporting P1 are mutex with all actions supporting P2, that means every pair of actions, one supports P1, one supports P2, are already marked mutex. So that is a pretty strong requirement. Okay, so for example, if P1 has 5 actions supporting it and P2 has 4, then there are 5 times 4, 20 pairs. All 20 pairs must be marked mutex before you say P1 and P2 are mutex. If 19 are marked mutex, one is not, that means P1 and P2 are still possible. Do you see what I'm saying? I mean, you won't say that something is not achievable because there are many, many ways of not achieving it. Right? I mean, you say it's not achievable because there is no way of achieving it. That you can fail trying to achieve it is not, a reason to say it's not achievable. Okay? So that's the negative interaction analysis. Okay? I'll go back from here to where I was previously. And I pretty much will come back to that slide and end. That's what we'll do today. Okay? Okay, so this is where we are. For now, actually, forget about the negative interactions, although you understood it already. For now, suppose one of the things I mentioned to you about heuristics, I think somebody asked, and I mentioned that in the case of heuristics, you can be as lazy as you want. Okay, so for example, you don't feel like doing planning graph with negative interactions. Okay, don't do it. If you don't do it, you'll be just less informed. You'll still be better than your friend who is doing set difference heuristic. If you throw in the negative interactions, you will be taking more time, but you will be more informed. Okay, and similarly, if you are trying to expand this graph and then it hasn't yet leveled off and you feel like having some lunch, you don't want to keep going any further. Fine, don't do it. That's okay. And what happens then? Essentially, if in the very last level, one of the interesting things about level off is, suppose I'm trying to see if a particular condition can be made true, and it's not even present in the last level, and the graph actually has leveled off, then you can assume its cost is infinite. And you won't lose admissibility. If on the other hand you didn't grow it all the way to level off because you were just lazy, then you can assume and the level of level is 15 and this guy is not yet there in 15. So what can you assume?
16.
16. Clearly 16 is significantly smaller than infinity. Right? But you get what you pay for. You're not thinking it's just 0, like what your friend might be doing, or just 1, like your other friend might be doing. You're still, better than, you're better for having done some work. Okay, so that's the beauty of heuristics. In the case of heuristics, you can be as lazy, as informed as you want, and that's why that picture is something that I like. You essentially, as you spend more and more time on the heuristic cost, you are increasing the computation cost of the heuristic. And then you're hoping that the search, and the search in fact reduces with more informed heuristic. But you don't really know where the minimum is. You don't really know at all. Okay, in some cases, people tend to think that, okay, this is where generally in practice it seems to occur, but there's no proofs. So if you are, all I can tell you is don't be too lazy. But don't be too eager either, because if you go all the way here, you will be in H star and you will be spending all your time doing the heuristic, and you will basically never win because you spent all your time in the heuristic computation. Way more than all your time in the heuristic computation. Okay? That's about the planning of heuristics, right? So going forward, and then I also told you that if you just have positive interactions, basically the way to use this for computing heuristics is if I have a single literal and I want to know, if a single goal and I want to know how far is it from the goal state, how far will it be for me to achieve that goal, I look and go to the first level where that literal is present and say that is the length of the plan, and that would be a lower bound heuristic. That's fine. If I have 2 literals, what do I do?
Max.
Okay, so if you have 2 literals, the interesting thing, actually max is a very beautiful point. So if you have 2 literals, you can do sum. If you have n literals, P1 to Pn, okay, and then the level at which P1 occurs is, let's say, L1. Level at which P2 occurs is L2, level at which Pn occurs is Ln. And notice that I'm using the same Ls. So this actually tells you that individual goals, the difficulty of individual goals can be separated in planning graph. Some goals come later, that means even if you have nothing else to do, they are harder to accomplish. Some goals come earlier, that means even if you have nothing else to do, they are easier to accomplish. That's just about themselves. Okay, and so now if I have L1, L2, Ln, then I can do H sum heuristic, which just says the cost of doing P1 to Pn is the sum Li. This will not be admissible if in fact there is any positive interactions between these literals. Right? Because the cost will be actually a little less than L1 plus etc. plus Ln, and so you would be dinged for not being admissible. Okay. The second idea is what somebody was saying, H max. And I'll also call it H level. H set level. The textbook calls it H set level. H set level is look at the first level where all of them are present in the layer. That would also be H max. Why? Because the guys who come in early will just hang around. Remember, this is a tenure system. The guys who come in early will hang around. When the last guy comes, then everybody is there. So H max is the same as H set level. Where H max will not be H set level is if you are considering mutual exclusions. If you're considering mutual exclusions, then it's much more interesting. Because then you essentially want to see the first level where the entire set is present and no pair is marked mutually exclusive. So if I'm talking about P1 to Pn, there are possibly n square mutual exclusions that can be marked. None of them should be there. Then I say, at least I have guarantee that every pair of these can be achieved, and so I'll assume that that is the actual cost. Do you understand what I just said? And that would not be H max anymore. Because the last level somebody comes in by itself, maybe 15, and there is the last level where all of them are pairwise non-mutex, maybe infinite. Right? For example, HC comes in last in, let's say, level 2, not HC comes in last in level 1. HC and not HC will never come in together. Right? And the set level heuristic will say they are infinitely costly. And it would be right. And if you just said H max, it will say that it's too costly. You would be admissible, but obviously very badly uninformed. Very, very badly uninformed. Right? Okay. Now, so that's the H max is sometimes equal to H set level, but really you think in terms of H set level because that idea also works for negative interactions. Okay. A third idea is to actually realize that the levels are not connected to the length of the plan. Because suppose I have, actually let me show you a picture. So suppose I can have, in the first level I have 15 actions, second level I have 12 actions. So I'll say the plan length is 2, but that's only number of levels. The total length is actually 15 plus 17. And so if you don't count, and since really after all the real planner cares about the number of actions, not just the layers. So if you don't actually count the plan length, you would be, uninformed. Okay, so what can I do? Okay, so here is a picture that I'll show you. Skip over this. I'm sorry, I'm skipping over the slides, but that's why the listening to the lecture is more useful. So consider these two examples here. Just made them up, okay, for making this point. In this case, there are B1 to B100 are the actions. Each of them, B1 gives P1, B2 gives P2, etc., B100 gives P100. And nobody gives anything else. So if you are considering the cost of, and for now ignore negative interactions. If you're just considering the cost of achieving P1 to P100, according to the set level heuristic, it would be 1. Because by the very first level, all 100 are present. According to the H sum heuristic, it would be 100. Who wins in this case, in this example? H sum is way better. Because not only is it admissible, it is also way more informed. But unfortunately, if you have the following, this different one, example, where P star gives P1 all the way to P100, H sum would say the cost is 100 because the cost of P1 is 1, P2 is 1, etc. P100 is 1. The cost of all of them together is 100. Okay, whereas H level would say the cost is 1, and this time H level wins. Because H level actually got the right cost and in fact is admissible. My question is, can I not be, in one case H sum is winning, in another case H level is winning? Is there a way of putting them together and get the right answer all the time? Now normally the right answer means doing actual planning. But if I'm not doing negative interactions, that means I have no mutual exclusions, then there is a cheaper way. Basically all I need to do is to sort of extract from the planning graph the plan that supports the goals that I need. That is extracting a relaxed plan. I call it relaxed plan because since I'm not having negative interactions, it's not a real plan. It would have actually been the real plan if actions didn't have any negative interactions in this domain. Okay, now how do I do that? I would basically say, here is the structure. In this level, I want to support every one of these guys. So these are all my goals at this level. So my search process is, in the previous level, pick one action for supporting each of them. And when I pick them, then in the level before that, all their preconditions become subgoals. Then I pick one action for supporting each of them. By doing this, I'm actually picking the actions. Okay? And then when I reach the initial state, then I have to pick the entire plan. And I just count the number of actions in the plan. That would actually work in both cases here. Right? Because here I would have picked all these guys as the goals, and this is the only one supporting, this is the only one supporting. So I would have to pick all of these, and then I reach the initial state. So the relaxed plan I picked is B1 to B100. All the actions. So if I count the actions in the plan, there are 100 actions. So I win. Okay? In this case, I have, I'll pick P1, I do P1 and I pick B star to support P1. Obviously only B star to support P2, only B star to support P3. Okay? And then I'll reach the initial state and I have picked just one action. This is called relaxed plan extraction. This is almost like doing planning, except way better, way cheaper. And the plans you get won't work in the real world. But their length is a good estimate on the actual length of the plan. Okay? Now, how costly is this extraction process? It turns out that you don't, all you wanted to do is find a plan, okay? You never have to backtrack. That means you can start from here, greedily pick actions supporting this, and then look at the preconditions, greedily pick actions supporting this, and continue and reach the goal state, initial state, and you would have a plan, and it will work. It's guaranteed to work, assuming there are no negative interactions. Much better than normal planning, where in fact you may have to backtrack because the actions you pick to support this goal and this goal may be mutually exclusive, so you have to pick a different pair of actions. So relaxed plan extraction is actually a cheap computation. It doesn't require backtracking. So that's why people actually use it. Okay? Now, if I do, then basically the only other thing is, suppose I have a crazier example where I have B star as well as B1 to B100 in the same problem. Right? I can make my life now more complex. So B star as well as B1 to B100 are in the same problem. Then, then too, I don't need to ever backtrack. But if I'm greedy and try to use the same action that I picked for supporting one goal to also support other goals if possible, wherever possible, then I would have picked just B star and I would have done still. Fine. Okay. In general, if I need proof that what I got that way is for sure optimal, unfortunately, I do have to do search. So finding a feasible relaxed plan can be done without backtracking. Finding an optimal relaxed plan requires essentially checking that no other relaxed plan is better than this. And that's NP hard. Okay. Now, so each set level. So now basically I have in this case, in terms of relaxed plans, I have each relaxed plan heuristic, and you can do it greedy, in which case it's not admissible. You can do it full search, in which case it will be optimal and it will be admissible. Now you would say NP complete, is bad, but in this course NP complete is good, because the actual planning cost is p-space complete, which is even worse than NP complete. I'm not saying that you should look for optimal relaxed plan, but if you're using relaxed plan heuristic and you want to guarantee optimality of the plan you produced, then you need to look at optimal relaxed plans, and those are NP complete to compute. There's no way out of it. Okay? Now, since I talked about relaxed plan, without positive interactions, what if I also have mutual exclusions marked and I'm computing the plan? Would it be any cheaper than normal planning? It turns out the moment you mark mutual exclusions, you cannot even get a feasible plan without backtracking. Because you pick actions at this level, and then you go here, you find that the sub-goals you're sub-goaling on are already marked mutex. That means you can't actually get them from here. So you need to go back and cut different actions and go forward again. And then you may go up to here. Then you find things are mutex. And you come all the way back here, repick, and keep going again. So in fact, I will send you an animation link which shows a program trying to extract an actual plan from this kind of a structure, when there are mutual exclusions, and it will do this fits and starts, come back, and then maybe sometimes it reaches all the way. If it doesn't even reach all the way, that means there is no plan of that length at all. Interestingly, I just changed discussion. I'm no longer talking about relaxed plans. If you have mutual exclusions marked, and you try to extract relaxed plan, what you get is not just a relaxed plan, it's a plan. Historically, and only in this course would be called 1995 historic. Okay. In 1995, the guy who came up with this idea of planning graphs actually came up with it as a way to do full planning, not as a way to do heuristics, but as a way to do full planning. And his idea was you essentially go mutex, basically you essentially go and mark the mutexes on the graph like this, and then start searching for a plan that supports the goals in this structure. Whenever you're unable to go forward because the sub goals you have are already mutually marked mutex, you backtrack. And if you're unable to find any plan at this level, extend it by one more level, search for a plan again. This is almost like iterative, deepening planning search on the planning graph. And that idea was called Graphplan. Okay, and Graphplan at the time when it came out was one of the fastest planners. And basically, a bunch of people figured out that actually, even though Graphplan is fast, it really can be understood in a better way as just providing heuristics. It is actually can be used as an approximate reachability analysis tool, so that you use it only as a heuristic and do normal search, state space search, like progression or regression. Okay, and to actually put this in perspective, how accessible these things can be, if you go to the text and look at the end of the planning chapter, you have these things like set level heuristics, and then most of this discussion actually comes from this course back in 2001, when we actually had a project of using planning graphs as heuristics in this class. Okay, and that's what basically, and that became more or less the main way of looking at planning graphs. Okay, so sometimes the ideas come for one reason and actually are more useful for a different reason. The planning graph was used to do explicitly searching planning graph to generate the plans. And yet, thinking of it as a relaxed reachability analysis tool winds up being way more useful. The current state of the art is to use planning graph as a reachability heuristic tool. Okay? And the last thing I want to tell you is, again, this is basically this picture. Here I was talking about relaxed plan extraction with respect to this picture. This slide tells you that same thing, step by step, except for a bigger example, for block fold example. Okay. First of all, notice that for the blocks world, remember that this one was a simple enough planning graph. The blocks world, you had 10 variables, right? And so if I draw forget about this. So if I draw the blocks world planning graph, it looks something like this. This is the first level. That's the second level. Right? So you need a really big piece of paper to draw this. But for your computer, it's just a bunch of pointers. It's just handling them. No big deal. Okay? So don't be surprised at how busy this thing looks. The question is how easy is it to compute this? It's actually linear time. And mutual exclusion analysis makes it quadratic time because you need to analyze pairs of mutexes. Those rules that I told you, those take n square time to propagate. Okay. And then, as I said, this is the relaxed plan example. So for example, if I wanted holding B and on-table B, let's say, as my goals, then I pick one action for holding B, one action for on-table B, let's say put down B. And then it turns out those actions will require only the same guy as the precondition. And then I pick an action to support that precondition, and I'm done. The stuff in red is the relaxed plan. Since there are no mutexes, I'll never have to backtrack. I can always get a feasible relaxed plan by just one greedy pass through the planning graph. If there are mutual exclusions, all bets are off. Because finding a relaxed plan that is correct with respect to binary mutual exclusions is finding the plan for the problem. It turns out. Okay. The last thing I'm going to say in the last 5 minutes is to make you think about how do these get used. By the way, this is H level, H independent, and H relaxed. That's what I was discussing here. There were slides. It's just I wound up using the board more. The last thing I want you to do is remember actually how these heuristics get used in the search, in the progression search. Okay, and that's where your mind should be kind of blending, because you'll do a lot of work. And yet, these are the winning ideas. I'm telling you, these are the winning ideas. Being lazy in heuristic computation is not helping. Being eager in heuristic computation helps, because the only thing that matters is the total time you spend. Okay, so here is a animation of how, so I'm starting again. I basically show you for whenever you have a state in the progression search, to compute its heuristic value, you start from that state, draw the planning graph, extract the relaxed plan, compute that length, and say that's H. And anytime you have more states, you compute new planning graphs from each of those states, compute relaxed plans for each of them. So if you think writing one of these planning graphs is painful, you're doing it once for each state in progression. Okay, so that's what this animation is showing you. So from P5, I drew this, and then I got a relaxed plan out of it. And then from P5, I got extra states. For each of these states, I'm drawing planning graphs. Drawing means computing planning graphs. And computing the relaxed plans from them, and taking the length of the relaxed plan as the heuristic value. In progression, you have to do this. Okay? So if you're doing progression, if you have 3 states here, and you want to see how far off each of these states are to the goal state, the only way you can do it is using relaxed plan. The planning graph ideas is compute one planning graph for this, one for this, one for this, and use your favorite heuristic, either H sum or H level or H relax. What matters is knowing what properties each of them have. H level is always admissible. H relax is not admissible if you do it for feasible plan, but if you do it for optimal plan, it is admissible. Okay? That's what you do if you're doing progression. One planning graph for each state. Okay. Now, if on the other hand you're doing regression, remember we were talking about regression yesterday, and this stuff should work for that too. If I'm doing regression, then what is interesting is each of these are the wish lists, the sub goals that I want to make true. I just need to have computed one planning graph from the initial state. Just one planning graph from the initial state. And I use, now if this one says P and Q, I look to see which is the first level where PQ occurs if I'm doing set level heuristic. Or what is the length of the plan that supports PQ if I'm doing relaxed plan heuristic. So if you're doing regression, you just do one planning graph from the initial state. If you're doing progression, you do one planning graph per state. So now tell me, which one do you think will win? Regression or progression? What? Regression, right? That's what I would think. It turns out progression wins. Right? So, just a second. Yes, go ahead.
Does progression win because it does more work in the heuristic?
The progression wins ultimately because of what we discussed yesterday. Progression starts from a complete state, and the states it gets are always consistent. Regression might be requiring, let's say, PQ. And if you are not doing negative interaction analysis, there may be a PQ present and so you think it can be done in 2 units or 15 units, but because of mutexes, actually PQ cannot be made true at all. So that may make you think, well, all you need to do is do mutual exclusion analysis, right? Unfortunately, that's not enough. If I have, let's say, P1 to Pn, and if basically I'm only looking to make sure that no pair of them are mutually exclusive, that's what mutex will make sure. If no pair of them are mutually exclusive, does that mean all of them can be achieved actually? No. Suppose I have a room for just 2 people. You all want to come into this room. He and he can come. He and he can come. He and he can come. He and he can. Every pair of you can come into this room. You try all of you coming in, it will be like that Egypt riot. Right? So now you will say, why not do a 3RE analysis? Let's see if the 3 people can come in. Then I will say, well, 3 can come in, 4 can't. Then you will say, do the 4 analysis. Then you say 5 analysis. Then you say 6 analysis. So that means you will start doing, to really get full information, you need NRE mutex analysis. That's too costly. You know, if 2RE mutex analysis is n squared, NRE mutex analysis will take n power n time. That's like H star. Okay, so you kind of can see how regression can come and bite you. But surprising is, unfortunately, in reality, you know, people actually tried this, including ourselves here. So progression need to compute a PG for each child state. So as many planning graphs as there are leaf nodes, lot higher cost for heuristic computation. That's true. Okay. And in contrast, in regression, you need to compute planning graph only for once for the given initial state. So much lower cost in computing the heuristic. The problem, of course, is in the case of regression, states in regression are partial states. So you thinking that P1 to Pn can be satisfied because by positive interactions alone, obviously is not enough. If you do negative interactions with mutex, that is you did n square time, that still is not enough. Okay, so you don't quite know how much analysis to do, and in fact, the more analysis you do, the more you're going into the fruitless portion of the costly heuristics. Remember, at some point of time, the heuristic takes so long to compute that even though search takes less after that, the sum is still quite high. And how do I know this? I know this mostly by history. People actually tried, using regression planners with planning graph heuristics, with mutex analysis. In fact, we had a paper on that, and some other people had papers on that. But, eventually, current state of the art is this wins over that. And you can improve this further by taking some negative interactions into account. The very current state-of-the-art planning is essentially taking a little more negative interactions into account on the progression side than starting from regression side. Okay, so this is the second part of regression, who wins. And it's not obvious. What matters is not who wins, it's the trade-offs that you understood as part of these discussions. Okay, so that's basically, so historically the heuristic was first used with progression planners, then they used it with the regression planners, then they again went back to the progression planners, and now we do progression planners with a little bit of negative interactions, which means a little bit of mutex propagation. And it actually turns out, in like 3 seconds, I can say that one of the smartest ideas that's going around right now is don't even do mutex propagation. Blow up the domain. Okay, maybe one person here will understand, and if so, I'm very happy. The idea of blowing up the domain is if the original domain had, let's say, literals P1 to Pn, that's it. Only those are the propositions. Now consider a domain where not only you have P1 to Pn, but every pair proposition is a new proposition. So P1, P2 is a proposition. P2, P3 is a proposition. P3, P4 is a proposition. P3, P1 is a proposition. So now you went from n state variables to n square state variables. And whenever you had an action previously which was giving P1 and P2, now the new action gives P1, P2, and P1, P2. And if you want P1, P2 to be true, look for P1, P2 directly, not P1 or P2. If you do this, if you blow up the domain and you only do positive interactions, no mutex propagation, you actually got negative interaction effect. Did you understand what I'm saying? Okay? Blowing up of the domain and doing positive interactions is like sticking to the old domain and doing negative interactions. If you do P1, P2, that is binary mutexes. If you consider P1, P2, P3 as a new state variable, that would be a ternary mutex analysis. I just reviewed a paper which talks about this, and it actually does even better than everything else. Okay, so we'll stop here. You should try to do the planning graph problems in the planning homework yourself. That's not required for the exam on Thursday, but it would be made as part of the next graded homework. And so that's the only way you know that you understood this. So when we come back, we'll actually change gears and go into propositional logic. Thank you. Thanks for your time.